Welcome back to our series on multivariable calculus. In this episode, we're going to look at Green's theorem, which gives us an opportunity to extend the fundamental theorem of line integrals to multiple dimensions. First, let's review what we've been working on. We've been looking at ways to integrate over a curved path, f dot dr, where f represented some vector field and dr a path through that field. Well, Green's theorem extends to a special subcategory of these where we're going to integrate over a closed curve. By closed curve, we mean the curve's going to take off, head around the xy plane, and then return to its starting point. We tend to refer to those using this notation. So that refers to the fact that the curve is closed in upon itself, that the beginning of the curve and the end of the curve are the same location. And another way to indicate that is just an integral over the derivative of d, the partial derivative of d. What this really means is that we're looking at the potential of taking an area integral and converting it into a line integral around the boundary of that area. And that's where the fundamental theorem of line integrals comes in. In essence, we were able to take a one-dimensional integral and turn it into a zero-dimensional integral, just the evaluation of the function at its endpoints. And of course, that involved the process of undoing a gradient. Well, suppose we've got a higher order derivative because we're actually going to do a double integral. Well, what Green's theorem allows us to do is to drop that double integral down to a single integral over a closed path. Here's what Green's theorem looks like, and then we'll talk a little bit about the implications of which side of Green's theorem we would choose to use. Here's the way Green's theorem begins. It's a double integral over some sort of expressed area within the xy plane. And it begins partial of q with respect to x minus partial of p with respect to y dA. So this would be an area double integral over the difference between the partial derivatives of these two functions p and q. Well, where do those functions come from? Well, the other side of Green's theorem gives us a clue on p and q. It's this closed loop integral over a curved path. And it refers to p dx plus q dy. And a way to interpret that is, this is just like our old friend the line integral. That is, we're just integrating it now over a closed path. So it's f dot dr, where f was the original function pq, and dr is represented by dx dy. If it's possible to do this with a parameterized version of the function r, then we can go ahead and go in that route. And that's certainly one way to evaluate any line integral. The problem is many of our functions f were conservative functions. And that basically means over any closed curve, the beginning point and end point are going to be the exact same value. And if in fact we could reduce this by undoing the gradient and turn this into a function where f actually represents the gradient of that function, then we would end up with fa minus fb, where a and b were actually the same location. And of course, that wouldn't work. So it gives us another path to evaluate this integral rather than applying the fundamental theorem of line integration. And that is, we can go ahead and take a double integral over an area and turn it into a single integral over a closed path. Well, let's talk about what those two things look like. And then you'll be able to see whether you want to manipulate these by taking partial derivatives or not. Well, suppose in general in the xy plane, we had some sort of a curved path that closed in on itself. Of course, all of our areas in the xy plane did this. They definitely had a boundary and then an interior, and this interior represents the region D. In each problem, we'll generally know what this region is. We'll have limits of integration in x and y. They could be functional or they could be integers, but we'll know what this region's shape and size is for this double integral. What Green's theorem says is that we can reduce this to a single integral, but instead of it being over the area, it's just going to be about the boundary of that area. So it would mean to trace the same area, except now we're going to take it as a curve, and we'd need a parameterized version of that curve, and we would have to integrate in a counterclockwise direction in order to match the conditions of Green's theorem. Well, clearly some path curves through the xy plane are fairly easy to integrate. A good example would be a circle centered at the origin. Be very easy to integrate that from 0 to 2 pi, and of course that would be in the counterclockwise direction, and I could actually build a vector function that would trace out that curve. That means I could integrate this directly, just inserting the functions for p and q, and then substituting if in fact I'm going to use polar coordinates. However, this curve may be very difficult to describe by a parametric equation, in which case it'd be far easier to simply integrate over the area. But for that, we would need to pull out our p and q functions from the result of the dot product of f dot dr, and then take the partial derivatives, dq, dx, dp, dy, take the difference between those, and then simply integrate over the area. What Green's theorem does is it provides you with options. You can turn almost any integral of area into an integral of path bounding that area, and correspondingly, you can turn almost any integral of path into instead an integral of area. Now, from the problems in this section, you'll see when it's a good idea to turn this into a path integral and when it's a good idea to turn it into an area integral.